When we think of steel, we picture strength, right? Absolute perfection. But what if I told you that every single block of steel is actually born from this chaotic battle against the laws of physics? Its journey from a fiery liquid to a solid chunk of metal is just riddled with hidden flaws.
I mean, from the outside, it looks completely solid, totally flawless. But deep inside, there's this dramatic story of cooling, shrinking, and purifying going on. So, what secrets are really locked away inside this seemingly perfect block? The answer? Well, it reveals the true nature of metal itself.
The simple truth is that transformation from liquid to solid, it's never perfect. The crazy part is, the very process that creates the ingot, the cooling, is also the thing that creates its biggest imperfections. And these flaws tend to fall into two very distinct families.
So on one hand, you've got natural defects. These are flaws that are just an unavoidable result of physics. They're part of the deal. Then, on the other hand, you have accidental defects, and these are basically mistakes caused by errors or other outside factors during the process. We're going to start by exploring the natural ones first.
Okay, so let's dive into part 1, natural defects. These are the flaws that are literally born from the physics of cooling. They're the ones metallurgists are constantly up against.
Our first and probably most dramatic natural defect is called retoucher, which is really just a fancy word for shrinkage. The idea is super simple. When things get cold, they shrink. And as that liquid steel cools down and becomes solid, it loses volume, and all that lost volume has to go somewhere, creating a big empty void inside the ingot.
So how does this gaping hole actually form? Well, check it out. The ingot starts cooling from the outside in. As those outer walls get solid, they start to shrink, and they pull in molten steel from the center to fill in the gaps. The liquid at the top literally feeds the solid parts below. But you can see where this is going. Eventually, the top runs out of liquid, and what's left behind? A massive, empty cavity.
And we're not talking about some tiny little flaw here. This shrinkage cavity can be so massive that the entire top section of the ingot has to be just cut off and thrown away. That can mean wasting up to 1/3 of the total weight of the ingot. 1/3! All because of this one totally natural process.
Now, this shrinkage problem leads us right into our next natural defect, segregation. So if shrinkage is all about a loss of volume, segregation is all about bad chemistry. The best way to think about it is like a melting slushy. You know how the pure water ice melts first, and you're left with that super concentrated syrupy puddle at the bottom? Well, steel does the exact same thing.
So as the steel starts to freeze from the outside in, all the junk, we're talking carbon, sulfur, phosphorus, gets literally pushed away from the solid walls. Because these elements have a lower freezing point, they basically retreat into the very last bit of liquid metal, which, you guessed it, ends up right in the center and at the top. This leaves you with a core that's impure and structurally weak.
And for our last natural defect, we have something called souffleurs, or as we'd call them, blowholes. And yeah, they're pretty much exactly what they sound like. They're just tiny pockets of gas, mostly hydrogen and nitrogen, that get trapped as the steel solidifies. They are literally bubbles frozen forever in solid metal. But here's the cool part. This is one where metallurgists can actually fight back a little. It turns out, by adding just a tiny pinch of aluminum or silicon to the molten steel, they can kick off a chemical reaction that basically soaks up these gases. It's a clever trick that dramatically cuts down on how many of these blowholes actually form.
All right, let's move on to part 2, accidental defects. Now, these are a whole different beast. Unlike the stuff we just talked about, these aren't baked in by the laws of physics. Nope, these are caused by human error, mistakes in the process that really shouldn't happen.
And here are two of the big ones you really don't want to see. First are creaks, which are surface cracks. Think of them like tears in the ingot's skin that happen when the surface cools down way too fast. But then you have tapors, or internal tears, and these are way scarier because you can't see them. They're hidden deep inside, caused by massive internal stress when the ingot is cooled or reheated too quickly.
And listen, it's not just about these huge dramatic tears. Sometimes, even the smallest little slip-up during the pour can leave behind a really dangerous flaw.
Take cold drops, for example. These are literally splashes of steel that freeze in midair and then just fall back into the molten mix. Not good. Then you've got sand inclusions. That's when bits of debris from the equipment fall in. It's kind of like getting eggshells in your cake batter. You just don't want them there. And ripples? Those are just ugly marks on the surface that you get from a jerky, unsteady pour. Every single one is a tiny mistake that can cause a big problem later on.
Okay, so we've gone through all these different flaws.
the natural ones and the accidental ones. But so what? What's the real-world impact? Why is it so incredibly critical to manage these things?
Well, it's because these flaws aren't just, ugly spots. They're not cosmetic. That hidden tear, that impure core we talked about, that can be the exact spot where something breaks under pressure, catastrophically. Honestly, understanding and controlling these defects is what modern engineering is all about. It's what determines the strength of a bridge, the safety of your car, and really the cost and reliability of almost everything around us.
So the next time you see a giant steel beam, or maybe just a simple tool, don't just see a solid piece of metal. See the incredible science, the intense battle against physics that went into creating it. And think about all those invisible flaws that had to be conquered just to make that one thing seem so perfectly strong.